Hi, everybody. Welcome to section 1.6, discussing average and instantaneous rates of change. So, at the end of today's lesson, students will be able to learn the very important definition of a derivative and learn how to take their first derivatives and its applications as rates of change, right? Students will see the connection between tangent lines. That's something we're going to learn today, and how it relates to rates of change, and find out how to find the equation of a tangent line. Okay. Students will see the geometric connection between a function's graph and its derivative, and students will learn the connection between differentiability and continuity, and when a function is not differentiable. Okay, so tangent lines and rates of change. So maybe you've seen a tangent line before, maybe seen it in your previous classes or a secant line. But let's go ahead and reintroduce ourselves to it. So far in this class, and maybe in your previous classes, we've been able to find an equation of a line given 2 points, right? So if we look at this graph here, we have 2 points, P, Q, right? Respectively, x1, f of x1, right? x2, f of x2, right? Just xy coordinate points. So with 2 points, we are able to find an equation of a line, right? We have our y equals mx plus b, right? We could find an equation given these 2 points, right? We find the slope, things like that. So what this actually is, this line between 2 points on the graph, this is actually called a secant line, right? That guy right there, that blue line, that's a secant line. Okay. So tangent line, what does that mean? So what if I just have this point P and I just want to find the equation of a line that goes through P, right? If I want to just find the equation of a line that looks something like that, it's bouncing off the graph, it's only touching that point P on the graph. How do I find the equation for that, right? So how do I find the equation of that guy, right? That's a line. So what that actually is called a tangent line, right? It's just touching that point P. But once again, in our past, we've only known how to find the equation of a line with 2 points, right? I have P, I have Q. I know what the equation of this line is, but I don't know how to find the equation of that line because I only have 1 point P. Okay. So there's ways to go about this. So we can estimate, right, the slope of this tangent line, right, at a point on the graph. In this case, it's P, by finding the slopes of secant lines at points closer and closer to that point. So you see here is Q, right? What if I keep choosing points closer and closer and finding those lines, right? Closer and closer and closer. Eventually, I'll get super close to P and it would almost be identical to that. Okay, but I know it's a little abstract, but let's keep reading through this. So we can estimate the slope of the tangent line at point P by finding the slope of the secant line that connects with another point Q, right? Here's Q, but what if I keep moving Q closer and closer and closer and seeing what that line would be, right? It's getting the closer you get to that point P, the closer you get to mirroring that tangent line. Okay, let's keep going. So what's the slope of the secant line, right? The slope of the secant line is simply the change in y values divided by the change in x values. Once again, it's just like rate of change, you know, your y2 minus y1 over x2 minus x1. Slope of the secant line, right? Okay, so that's how we find the slope of a secant line, right? That's how we would find this guy right here. But yeah, we want the tangent line, right? Not the secant line. So once again, the idea is, what if we make Q just get closer and closer and closer and closer to P, right? Make Q closer and closer to P. That's our goal. So let's go ahead and scroll to the next page. And here's a more definitely annotated graph that helps us with that concept, right? Say you start out right here. Let's call this Q1, right? Q1, right? It's coming over here. This is some type of secant line, right? But once again, I want the slope of the tangent line here. in pink. That's a tangent line. That's a point, or that's a line that's just touching that point P, right? I want that line. So once again, I'm just going to get Q closer and closer, right? Call this Q2, call this Q3, right? So I'm getting closer, closer, and closer, right? Eventually, I'm going to get a point like right here in purple, and I can just, it's getting really close, right? Okay. Let's get closer and closer, and that way we can kind of get that mirror of that. So if we want to know the slope of a tangent line, right? And synonymous with tangent line is instantaneous rate of change. So think about it, right? When we look at rate of change over an interval, right? It's always like over some type of interval from like P to Q2, right? Some type of rate of change, but instantaneous rate of change is the rate of change that's happening right at that instant, right at that P. It's not happening over any other interval. It's happening right at P. That's why it's called instantaneous, where it's only at that one point. So I'll say this instantaneous only at that one point. It's instant, right? It's not over some interval, it's instantly at that one point. But okay, so what if we take the limit of all of these secant lines as I approach that point, right? So we can take as many points as we want, but the way to go about it is arbitrarily just get infinitely close to that point, right? We can't ever be at that point. We can get really, really close, infinitely close. And that's why we take the limit. Okay, so that's kind of how secant lines relate to tangent lines, right? So here's some kind of vocabulary to go about it, right? Average rate of change is just your secant, right? Secant, just your regular. We've done this before. Average rate of change over an interval, right? But then the new thing we're learning is instantaneous rate of change, which is your tangent. Well, we're taking the limit, we're getting infinitely close to that P. So that's why we're taking the limit. And it's the same kind of formula as average rate of change, but this time we're taking a limit. Okay, but here's some more mathy notation, right? Average rate of change, still talking about the same thing, but you know, we have f of x plus h minus f of x over h, right? And then at instantaneous rate of change, we will have this formula right here, as opposed to we have this limit now, okay? Because we're getting really, really close to that point. But okay, so find the average rate of change of the function f of x equals x squared plus 7x on the interval 2 to 6. So average rate of change, we definitely know how to do this before. And we're going to use this one. I don't want to use this formula here. Let's just keep it simple like we've already known before. So average rate of change of that function on the interval. So what you would do here, average rate of change of f of x over the interval from 2 to 6, right? And so remember our average rate of change formula is just f of, x2 minus f of x1 over x2 minus x1. And, just in case, this is your x1 and that's your x2. All right, so what this becomes is just f of 6 minus f of 2 over 6 minus 2. And so now it's just plugging in 6 and 2, getting our outputs, and finding out what that answer is. So let me just go off to the side here and write f of 6 equals 6 squared plus 7 times 6, which is 36 plus 42, which is 78. Okay, and f of 2 is 2 squared plus 7 times 2, just 4 plus 14, which is 18. Okay, so that's my side work. Let me go ahead and plug these guys back into the equation. So I have 78 minus 18 over 6 minus 2. All right, so that's just 60 over 4, which just equals 15. And that's my average rate of change over that interval. Okay, so that is how you find average rate of change, just like we were doing in the previous section. And here's a big new concept now, instantaneous rate of change. All right, so this is, we're not finding it the rate of change over some interval, right? We're just finding it legitly at that point, x equals 2. So specifically, right at that point, not over some interval, it's instantly at that point, that instant. So what we're going to do is the math way to go about it. I want to show you two different ways, but let's go ahead and try out the math way, where we're going to take a limit, right? That's why we learned limits before, and kind of see how this all works together. So the first way, like I'll say, using definition. All right, so the instantaneous rate of change at of f of x at x equals 2, which is going to be the limit as h goes to 0, just using this formula up here of f of x plus h minus f of x all over h. Okay. Okay, so what we have here is the limit as h goes to 0, right? And I know what my x is. My x is 2. So I'm going to plug in 2 for x. I'll make that mark here, right? So this becomes f of 2 plus h minus f of 2 all over h. Okay, so what this means is that this 2 plus h and this 2 are inputs. So I need to plug in this guy into there and this guy into there separately though, right? So what I want to do here is go off to the side and do some scratch work. Or, here's what we'll do. I'll write it out and then we'll do some scratch work after that. So this is limit as h goes to 0. And then I'm going to plug in 2 plus h into wherever there's an x. So I'll have 2 plus h. I'm going to put brackets. 2 plus h squared plus 7 times 2 plus h. That's this part right here where I'm plugging in 2 plus h wherever there's an x. Minus brackets again, 2 squared plus 7 times 2. And don't forget, we're all over h. Okay, so I'm going to go out to the side and do some scratch work for this guy, this 2 plus h squared, just so it won't get all jumbled up in there. So let me do some scratch on the side. All right, so 2 plus h squared is 2 plus h times 2 plus h. And then if I multiply that out, it's 4 plus 2h, and h times 2 and h squared. So plus 2h plus h squared. So that just equals 4 plus 4h plus h squared. All right, so that's my scratch work. Let me go ahead and put this guy back in there. So this equals limit as h goes to 0 of 4 plus 4h plus h squared. The 7 gets distributed in, plus 14 plus 7h, right? That's that first part, minus 4 plus 14 all over h. Okay. Now, let's just go ahead and simplify a couple of things coming down here a bit. All right, so we have a couple of like terms. We have 4h, 7h, 4, and 14. And then we can combine that 4 and 14 over there. This equals 18 plus 11h plus h squared minus 18 all over h. Okay. And so this becomes a negative 18, right? This becomes minus 18. And so that cancels out with this guy. All right, so what we're left with is limit as h goes to 0 of 11h plus h squared over h. So kind of drawing it back to beginning, the reason why we can't plug in h goes to 0 right away is because we're going to have a 0 on the bottom, and that's a big no-no, right? We can't have a 0 on the bottom. So we're doing all this algebra in the meantime to be able to cancel out this h in the end, which will happen right now. So, right. So what I can do is factor out an h from here because they have an h in common. I can take out an h, right? H comes out, so it's just 11 plus h over h. And now these h's can cancel out. So I'm left with limit as h goes to 0 of 11 plus h. And now it's okay to plug in h because I'm not going to have a 0 on the bottom. So I'm going to plug in that h. The limit goes away, and I'm just going to end up with 11. So this is the instantaneous rate of change of f of x at x equals 2. Okay, so that is how to find the average or instantaneous rate of change using the definition of derivative, right? This limit definition here. But if that is just too confusing to do, right, it's a little too abstract for you, and you might not understand completely what's going on. There's also another way to find instantaneous rate of change. It's an approximation. It's not exact like this because this one we're mathematically doing it, but there was also a way to do it that's a little less complicated. So the second way I wanted to show you guys is using your average rate of changes. So here's, I'm just gonna make a second page to find instantaneous rate of change using average rate of changes. So what does that mean? So since we're checking out at the point x equals 2, what I want to do is find a couple average rate of changes around x equals 2 and then average them out. So I want to find an average rate of change from, let's say, 1 to 2 and from 2 to 3. Just pick intervals around 2. Okay. So what I'm going to do is find the average rate of change of 1 to 2 and 2 to 3, and then average them out. Okay, so what does that mean exactly? So let's go ahead and try it out. So average rate of change of f of x over 1 to 2. Remember, average rate of change is f of x2 minus f of x1 over x2 minus x1. Okay, so the way we do this, right, this is just f of 3 minus f of 2 all over 3 minus 2. So recall that f of x equals x squared plus 7x, right? So we're just going to plug in 3 and 2 into this guy and figure out what that is. So we get, maybe not enough room, we're going to come over here. So we get, 3 squared plus 7 times 3 minus 2 squared plus 7 times 2 all over 3 minus 2, which is just 1. Well, I'll write 3 minus 2 here. Okay, so that ends up being 9 plus 21, so that's 30, minus 4 plus 14, that's 18, right? So we get over 1, so that's 30 minus, 30 minus 18, that is just 12. Okay. So 12 over 1, which is just 12. Okay, so that's the average rate of change of f of x over 1 comma 2. Now let's go ahead and find it for 2 to 3, and then we can average them out. So same exact thing, average rate of change of f of x over 2 comma 3. Okay, so same thing, f of x2 minus f of x1 over x2 minus x1. So that's just f of 3. You know what? I did this one on accident. Excuse me. But let me just erase this. So I accidentally did 2 to 3 on accident instead of 1 to 2. So this one is 2 to 3. And so this one I'm going to do 1 to 2. My apologies. Okay. So once again, we're finding the average rate of change from 1 to 2. So it'll be f of 2 minus f of 1 over 2 minus 1. Okay, so f of 2, we already just found that, right? We found f of 2 to be 18. So this will just be 18 minus f of 1, which is just 1 squared plus 7 times 1 all over 2 minus 1. So this is 18 minus 7 over 1. I'm sorry, not 7. It should be 8 minus 8 over 1, which is just 10 over 1, which is just 10. Okay, so now is the last part where we just average them out. So we just take the average, right? So it would be 12 plus 10 and we divide it by 2, which is 22 divided by 2, which is just 11. And look at that, 11, and that's the same thing we got when we did the whole definition limit. Okay, so there's two ways to go about it. One is using the definition, mathematically doing it, or there's one where you're kind of approximating with average, finding the average rate of change of intervals around it, right, to get that instantaneous velocity. So recall this is just your instantaneous rate of change at x equals 2. Same answer, just different ways to go about it. This one is a little more work, right? but whichever you prefer, you'll get the same answer. Okay, or at least a close approximation. But that's it for 1.6. There's a couple of practice problems here if you want to check it out or just do the homework. But other than that, thank you. We'll see you next time.